So far, we've seen several properties of waves. We've studied the reflection of waves in strings, and we've studied the interference of waves in strings and in sound waves, and we'll study later on refraction of light. Now we're briefly going to introduce the diffraction of waves. So in particular, let's take a look at what diffraction of waves will be with water. So you can see there's a wave coming along through here like this, and as it passes through this opening, it seems to bend around that little narrow opening. You also can get this with sound waves as well. So what is diffraction? Well, diffraction is the bending of a wave when it goes through an obstacle or an edge, passes through that region. So it's a bending other than means of reflection or refraction. It's a new type of bending of a wave, and it occurs when that wave passes through a narrow opening, all right, which causes the wave to spread out or diverge. So I'll be showing you a demonstration in class, something like this picture over here. We'll have a ripple tank, and we'll make some plain waves, these waves that are nice straight lines here. And we'll produce patterns to show you where you get pronounced diffraction and not so pronounced diffraction. When these waves move through a barrier that's quite wide opening, so this distance d is quite large, we'll find that the waves seem to go straight through with a little bit of bending that occurs on the side. The wavelength, which is the distance from one wavefront, which is this long line here, this is known as a wavefront. So right here, and then the distance from one wavefront to the other wavefront is called the wavelength. And the wavelength remains the same. What happens is you get a little bit of bending on the side. So the bending is very small at this point. However, when you make this distance d very, very small here, that opening quite small, then you start to see really pronounced diffraction, something like the following picture. So as that opening is more narrow, now you see a lot more spreading occurring here. So let me add into this picture now. And the wave starts to really just move in all the different directions here. It diverges in all the directions here. Which means if you were standing over here or over here, you would be able to that wave would reach you. Maybe over here, it's not going to reach you right on the edges here. So this is an important thing because, you know, maybe you are aware that some waves can bend more easily than others. Like sound waves can bend more easily around corners than, say, light waves. Why do you think that's true? Well, you see that this wavelength right here and this distance d, the d has to be smaller than the wavelength for you to get diffraction, or it could be approximately equal and you get diffraction as well. So the opening size is important, that size distance and the wavelength, that comparison. That if the opening size is quite large compared to the wavelength of the wave, then you don't get any diffraction really. So, and with light, for example, light has a very small wavelength. Um, and because it has a very small wavelength compared to sound, this has a larger wavelength, um, then light waves are hard to diffract because you have to really force light to go through a very tiny opening for you to see this bending to occur. It does occur, it's just you have to have that opening very, very small. Sound waves, on the other hand, have a much larger wavelength, so they can easily bend around obstacles and go through larger openings, and you can basically hear the sound even though you don't see it. Or should I say, see the source. And also, in this picture here, if the opening size is about the same as the wavelength, then you're also getting diffraction around here. It's just not as pronounced as you would get if the opening was smaller than the wavelength of the sound or the wave that's produced. This is just serving as just a sort of a conceptual introduction of diffraction. We'll be studying diffraction in a lot more detail with light waves. Let me show you a few animations just to kind of top this final little talk here. So here's a sort of a picture schematic to show you the diffraction through a slit. We have a slit that's quite large right now and the waves are coming through, and so here you can see with a large opening, this is what's happening with the waves as they pass through. It's not as much pronounced as diffraction, a little bit of bending over here, and really you can see hardly the waves are reaching on this side over here. Now I'll move it to a medium slit here and let the waves pass through here, and you can see this is now you're getting a bit more diffraction occurring over here. And now we have a small slit opening here, and the waves are passing through here. And now you can clearly see these waves are bending around here, and you get really pronounced diffraction here. Here's a different animation showing you what's happening with the water faucet dripping into a ripple tank here. It looks like this from the side here. You can see the water as it drops in here. You can show the graph of what's happening to the water level here. If you were to increase the frequency of those ripples of the water, you could see that the waves will get closer together, shortening the wavelength. Let's go back to our earlier view here. You can see that bright lines and dark lines correspond to those troughs and crests, and the distance between one dark line to the next dark line, or one bright line to the next bright line, is known as the wavelength. So if I increase the frequency, you can see the distance between them gets smaller. Now, I'll be showing you in class something like this, and we can actually also show interference. If we were to make this a two-droplet situation here, we have two sources, like two speakers, you get this interference pattern where you have constructive and destructive interference, and you have nodal and antinodal lines. We'll get into that and talk about that in class. But let's actually talk about, go back to one drip here, and let's add in a barrier. We have a slit here. And we'll just move this, we'll open up the slit quite large, move the slit over here, and you can see that you're getting not really anything happening. But if you were to make the slit quite small, and well, we got to make it small enough for the wave to get through, I guess, you can see now there is the diffraction, very pronounced, as you can see through here. You can get the same thing that occurs with sound waves. Let's take a look at the sound waves. There's a sound wave. There's a speaker producing this sound. If I increase the frequency, you can see this diaphragm thing is moving back and forth more frequently. And we were doing this last time when we talked about interference of sound waves. You can put two speakers producing sound waves here, and as long as they're in sync with each other, same frequency, in phase with each other, you'll get this interference pattern that is occurring over here, where you get bright lines, and then you have dark areas as well, where you have constructive and destructive sound. But going back to one speaker to show you what diffraction would be, let's increase this frequency a little bit more here. And then we'll add in a barrier and bring it in here. And you should see some diffraction occurring here. There you go. There's the diffraction occurring. And of course, if I make the spacing a little bit closer in here, you should see that it should become more pronounced, the diffraction. And lastly, you can do this also with light. So I click on the light tab here, and the light corresponds to, here's the visible light. We have red, which is a long wavelength in here. All right, you can see the wavelength in here, but if I go to, say, violet over here or blue, the wavelength gets smaller because you have a higher frequency. And you can get diffraction with light as well, forcing the light to go through a barrier, and you have to make the slit width quite small for you to see that diffraction. And the reason for that is the wavelength of light is quite small already, and so you need that opening to be very small. Okay, and that's our introduction of diffraction.